Welcome to the Researcher Zukan. Today I am at the High Energy Accelerator Research Organization to meet Dr. Kenji Saito. Nice to meet you.
Nice to meet you.
Dr. Saito is currently working on superconducting cavity technology for International Linear Collider project. I guess this is a model of the superconducting cavity you're working on. Could you please explain to us what kind of research this is?
Welcome to KK for everybody. I'm working on superconducting cavity for 25 years. Currently, I'm concentrating to develop high gradient cavity for the IRC. First, I would like to explain briefly about what is the IRC. IRC is a machine to discover Higgs particle. This machine is a very much complementary machine with the LSC, which will start operation in this year. This machine, we hope, discover the Higgs particle. LSC will concentrate on investigate more detail in this particle.
So, could you please tell us about this ILC, International Linear Collider project?
Yes. This is a schematic graph for the ILC. ILC is an electron-positron colliding machine which collides these particles at the center of mass energy 500 GeV. In the scale of the total length is about 30 km. It's a very huge machine. So this machine will be constructed by the purely international collaboration. In the tunnel, we install this kind of the cryo module, totally 1,700 cryo module we needed. Each cryo module includes 8 cavities. Okay. So next, please. This is a picture of the IRC cavities. Top is a now base design cavity shape, which developed at DAISY.
DAISY is a German institute.
Yes, and this cavity which produced 35 megavolt per meter at the acceptance test. Then we operate 31 megavolt per meter. But now we are proposing other cavity shape as an alternative cavity shape, which can produce much more higher than 40 megavolt per meter. This high gradient brings several benefits. We can reduce the total tunnel length. Then we can get cost reduction.
In developing the superconducting cavity, you have developed many key technologies, I heard. Could you please describe to us some of the technologies that you have?
Superconducting has 2 nice features. One is we are using the superconducting material, so surface resistance is very small, and this brings to the very high energy transfer from the microwave to accelerator beam. Other feature is we can choose conventional frequency because of such a high efficient transformer. So, but the superconducting is a very sensitive on the defect. So at first we have to use reliable material. Now we are using the niobium, pure niobium material. Okay, so this is now we can buy from the industries. And the next one, cavity should have defect free. Okay. If cavity has a defect, cavity gets heated, and then finally cavity quench. So for this technology, we have to use a mechanical grinding. Currently, we developed a centrifugal barrel polishing. And third one, we have to finish very smooth surface from point of the RF application. And electropolishing is a very good technology. And finally, we have to eliminate the particle contamination. Particle contamination sometimes bring the field emission or multipacking. For reduce this particle contamination, high pressure water rendering technology is very good. So totally reliable material, defect-free surface, and smooth surface, and clean surface. This is very much important for the superconducting cavity to get the high performance.
I see. I heard that this electropolishing technology was developed by you when you were a postdoc,
Yes.
and now it's a global standard.
Yes.
That sounds very neat. Could you please explain more about this?
This is a electropolishing system which was developed for the tristan cavities that are very huge cavity, because we choose 500 megahertz. Okay. This technology was developed by the very close collaboration with the company Nomura Plating, which located in the Kanuma city, close to in the Tochigi prefecture. In this system, electropolishing flowed in the cavity, and the cavity is applied plus voltage about 15 volts, and inside we put the cathode by the pure aluminum. Then electropolishing is opposite process from the electron plating. Niobium is dissolved by the applied voltage. Then inside we can get a very smooth surface.
I see. Now it's used for so many accelerators around
Yes.
the world. That's very exciting. Now, could you please tell us the future research that you aim at now?
So IRC is a very huge machine. So if we fail, if we rework, it's a time consuming and the cost is increased. So very stable, very reliable cavity performance is a very important issue. So now we are developing, produce such a very nice cavity performance with a very high production yield. Okay, so this now we succeeded to produce such a nice cavity performance, 45 megavolt per meter at a Q higher than the 8 times 10 to 9 by the single cell cavity R&D.
And secondly, you apply that to 9 cell?
Yes, now we enhanced such a nice preparation method for the from the single cell cavity study, but not yet demonstrated this technology how works on the 9 cell cavity. So near future we have tested this new recipe for the 9 cell cavity and demonstrate such a high gradient 45 and Q higher than 8 times 10 to 9.
Also, you plan to do a seamless cavity technology.
Yes, this is related to the cost reduction. Now superconducting cavity is still too expensive because we are starting the niobium sheet and the press and trimming and electron beam welding. Now we have a nice idea to reduce this complicated procedure. Seamless technology is a candidate. So now we are starting this technology.
In these future works, are there any possibilities that researchers from other fields could collaborate?
Superconducting surface is very much sensitive on the contamination. To get a high cavity performance, we have to understand this contamination issue. I'm coming nuclear physicist. I'm not expert in this field. So we need a lot of help from the chemistry.
And also? seamless.
Seamless technology. Now we are going to this technology. Of course, we are not so experienced for such a metallurgic. So we need a lot of help from the metallurgical engineers.
Sounds very exciting that researchers from various fields could possibly collaborate at the very frontier of particle physics. Well, thank you very much, Dr. Saito. It was very exciting to talk.
Welcome. Bye-bye.
Bye-bye.